Hi, I'm Janak Goyal. I'm a rheumatologist, and in this presentation, I will talk about very essential concepts of sonographic physics. Basic understanding of ultrasound physics is important for multiple reasons, including the creation of good quality images, understanding artifacts, and avoidance of adverse effects of sound on the tissues. Sound is created by the movements of particles of a medium, and it is transmitted through the medium by the waves of compression and rarefaction of its particles. The ultrasound transducer contains an array of piezoelectric crystals. The piezoelectric crystals vibrate when electrical current is applied to them. On the other hand, they generate electricity when they are mechanically deformed. And depending upon the clinical situation, the transducer is operated to produce either a pulsatile sound or a continuous sound. These are parameters used to describe the sound wave. The parameters used to describe time and distance are speed, wavelength, period, and frequency. And the parameters used for strength are power and amplitude. In this presentation, I will discuss only frequency and will not discuss other components further. The frequency is a number of waves per second expressed as hertz. 1 hertz is 1 wave per second. For medical ultrasound, we deal with millions of waves per second expressed as megahertz. So 1 megahertz is 1 million waves per second. So what is ultrasound? The sound is classified based on human audible range of frequencies. The human ear can hear a sound between 20 Hz and 20 kHz. So any sound with a frequency above 20 kHz is ultrasound. So here is a little box showing you all the classifications. The audible sound between 20 Hz to 20 kHz, the ultrasound more than 20 kHz, and the medical diagnostic ultrasound usually uses frequencies between 1 and 30 megahertz. Here is your transducer and here is your sound beam. After exit from the face of the transducer, sound beam progressively narrows to the half of its diameter. After the focus, the sound beam progressively widens as it travels to the deeper areas. The focus is the narrowest point of the beam diameter. The part of the beam from the transducer face to the focus is known as near zone or the Fresnel zone, and the part of the sound beam which extends from the focus to the deeper areas is called far zone or Fraunhofer zone. The focal length is the distance from the transducer face to the focus. It is also called focal depth or near zone length. The focal zone is the region around the focus where the beam is relatively narrow. The half of the focal zone is located in the near zone and half of that is in the far zone. Let's look into one of the most important issues which we always talk about is resolution. So what is resolution? A resolution is the distance between two signals or objects which your equipment, in this situation the ultrasound machine, could detect. Smaller the difference and better the resolution. Let's look into this example. Here I have arranged 9 different objects, but what you're looking at here, you see only 3 objects, and in this one you're looking only the 6 objects. So this is this distance of 1 millimeter, 2 millimeter, 3 millimeter, 1 millimeter, 2 millimeter, 3 millimeter, 1 millimeter, 2 millimeter, and again further they are arranged in the same way. Now, if your equipment has a capacity to resolve a 1 millimeter difference, then it will show all the 9 objects separately, and it's a high resolution machine. On the other hand, if your equipment cannot see a distance of 1 millimeter but can see only the distance between 2 and 3 millimeters, then these 2 objects will look as a one object. So you will see only 6 objects and this is a resolution which is less than what you have in this situation. On the other hand, if your equipment still cannot see a distance of 2 millimeter, can see a distance of 3 millimeter, you will see only 3 objects. So here is your equipment with a low resolution, here is kind of in between, and here is an equipment with a high resolution. Let's look at the various types of resolution. The resolution is defined as a spatial, temporal, and contrast. The spatial resolution is the resolution in space, basically is a grayscale resolution, whereas the temporal resolution is the resolution in time and is determined by the frame rate. And the contrast resolution is the resolution which measures your brightness of the signal and compares the different brightnesses. Now, as far as the spatial resolution is concerned, there are basically 2 components of the spatial resolution. One is the resolution of your screen, which is defined in terms of pixel density, which I'm not going to be talking about here. And then there is a resolution which is the resolution of the grayscale signal within the pixel. That's what I will be talking about. Here, the spatial resolution which I have listed, I mean the resolution within the pixel, and that is further considered as axial, lateral, and elevational, depending upon the direction of measurement. If you are looking at your resolution along the depth of your tissues, that is called axial resolution. But if you're looking at along the long axis of your transducer phase, and that resolution is called a lateral resolution. And the resolution along the short axis of your transducer phase is elevational, which is most of the times not seen on your screen because the beam has 3 dimensions, but the image on the screen has only 2 dimensions. So what we'll be looking at when we're looking at the image, we're just looking at the axial component, which is along the depth, and we're looking at the lateral component, which is along the long axis of the face of your transducer. Let's look into the axial resolution. Now here is your transducer and here is your sound beam. Here is the resolution along the depth of the tissue is called the axial resolution. The axial resolution is improved by higher frequency sound. Now let's look at your resolution along the face of the transducer, which is called lateral resolution. Now what I said, the lateral resolution is equal to beam width. Now look at your beam. What is the narrowest diameter of the beam? It's the focus. So the beam width is narrowest at the focus. That means your lateral resolution is better at the focus. So the focusing improves your lateral resolution along the face of the transducer. Focusing does not improve axial resolution. So the axial resolution is improved by higher frequency sound. The lateral resolution is improved by focusing.